Hello, and welcome to the presentation for CanCoach, Vehicular Control Through Human Cyber-Physical Systems. I'm Matt Nice, your narrator and the lead author of this work. This title slide just sets the scene. A cloudy day outside the Institute for Software Integrated Systems in Nashville, with real-time readings off the car's stock radar system. Take a second to watch as cars go by. You can see how the radar tracks the car as it goes down the road. Let's start by taking a look at why we're researching transportation. There are massive costs for modern transportation systems. Over $88 billion in economic productivity is lost due to traffic congestion alone. Transportation is the largest source of greenhouse gases, with the lion's share coming from passenger cars and trucking, and over 36,000 lives are lost annually in vehicle-related incidents. As traffic engineers, we come up with solutions to reduce or eliminate these costs. But it can be challenging to do full-scale field tests. Why? Because of the cost. Take this somewhat contrived Niagara Falls analogy. There are a ton of brilliant solutions bobbing in the Niagara River, but they can't make it intact through the falls/field testing into the real world. Why not? Well, if you have a need for advanced actuators for a control policy, you need to have access to multiple automated vehicles, and that's generally prohibitively expensive. With that said, there are many research groups that are doing experimental CPS work with AAVs. In the Arizona Ring Road experiment, researchers used an autonomous vehicle to run their wave smoothing algorithm, and it really worked. But what do you do if you want to scale this up to a full-scale open road test, and you don't have tens of millions of dollars, lying around? Well, that's where this paper fits right in. Our research question was, can a human driver with extrasensory feedback drive better than a human driver without it? Because perhaps you could make an HCPS actuator that could be used in place of an expensive AV. So we test out our HCPS with longitudinal control, because controlling speed and spacing opens the door for things like wave dampening, energy efficiency, and safety improvements. Having a human, computer, and vehicle integrated together constitutes an HCPS, as long as the three are integrated in a non-trivial way. That means each must be non-trivial in the function of the system. A classic example of an HCPS is an airplane pilot with an aircraft and the computer systems. The pilot must have a grasp of the emergent complexities in timing, control, and deeper understanding of principles of aeronautics. We'd like to see if it's feasible to do bulk traffic control with our car HCPS. Which brings us to the contribution of this work, which is a driver with extrasensory feedback, constituting an HCPS that can drive with superhuman precision for longitudinal control tasks. Superhuman being defined as improving driver performance operating as an HCPS compared to the human operating in isolation. First thing we need to do if we want to make this human CPS actuator is to scale down the cost dramatically. You're looking at VU1, our lab vehicle. With a Raspberry Pi and a couple $100 in vehicle interface hardware, we created a scalable, lightweight, open source setup that records high fidelity data, for example radar data, as well as everything else in the CAN bus, and is orders of magnitude cheaper than previous alternatives. Here's a demo showing the radar data tracking the relative velocity and space gap of the car ahead and the car in the right lane. In the left plots, we visualize the relative velocity data, and on the right, the space gap. The top left plot shows the relative velocity to the lead vehicle as a function of time. The bottom right replaces time with lateral distance from the vehicle. The time axis is now going into the screen. So with this CPS innovation, we can see what's going on in the car, but remember the core motivation. We want to know if we can create this HCPS actuator that could be used to change bulk traffic flow. So, here's a model showing how car following works on the roadway. The lead car provides input to the following car. The human driver presses on the brake or accelerator, and at a low level, it's implemented with a CAN bus. We ran a series of experiments to see if closing the loop and giving continuous feedback could give the human pilot the ability to precisely follow a longitudinal control task. First, was giving the driver instruction on the given task with feedback as normal from the lead car. Then, we add in the CAN coach. With the same control task, the driver is given continuous feedback. CAN coach is the system that reads, processes, and filters the sensor data from the CAN bus in real time, and then gives actionable feedback to the driver to adjust their speed and spacing. Lastly, we have ghost mode. In ghost mode, the car is virtualized, and the driver is following the control task without seeing the car ahead. This serves two purposes. One, to test the impact of the human in the loop. If they have a non-trivial contribution to the control loop, such as perhaps learned intuition of inter-vehicle dynamics, then ghost mode will result in worse performance. 2. To see how abstract of a task we can push the driver to accomplish. If they can precisely follow a car they can't see, then that's a very good sign for the flexibility of this system. Now for more details on the experiments we ran. Here's VU1 in action on the highway in Nashville, with its own dash cam in the top corner. Let's define a few terms to establish the language to talk about the two-car system. First, there's ego vehicle velocity, V, lead vehicle velocity, V lead, and space gap, S, which is the space between the two. Then there are the values derived from these variables. Time gap, tau, which is S over V, relative velocity, which is the difference between V lead and V, and the time gap error, which is the difference between the desired time gap and the instantaneous value of the time gap. Finally, I'll touch on the control objectives we tested in our experiments. There is constant time gap, having the driver maintain a static ratio between the speed and spacing. Velocity matching, where the driver matches the velocity of the lead car. This objective doesn't provide an explicit spacing constraint. And dynamic time gap, where the target time gap changes every minute. This table is just an overview of all of the tests we did for each of the 6 drivers in this study. There are varied modes to test the effect of the feedback on the driver. And there are varied driving objectives to show the flexibility of the system. Remember this table as we examine the results. Results section. We'll start with constant time gap. Here's the distribution of the driver's time gap error with instruction only. They're all over the place. Now look at the distributions of time gap error with CanCoach. They're all aligned tightly right over 0 error. This shows an HCPS CanCoach that's effective in achieving precise control objectives. Let's look at those plots in table form. The mean error drops massively from 0.44 seconds to 0.05 seconds. For scale, that's half the time of the average eye blink. We have drivers being given a speed and spacing control task at highway speeds, and with the help of CanCoach, they're off by less than the blink of an eye. So what about ghost mode? Well, ghost mode triples the mean time gap error across all drivers from 0.05 seconds to 0.15 seconds. And the story is the same for standard deviation. These increases in mean and standard deviation mean that when ghost mode is activated, there's diminished performance. Diminished performance means human vision is creating a non-trivial contribution to the control, the successful control, of the vehicle. As expected, when coaching for velocity matching, there was limited control of spacing. This is in stark contrast to constant time gap, where the spacing was consistent across all drivers. The range of mean space gap for drivers under coached velocity matching was about 30 meters, compared to about 5 meters with time gap feedback. In dynamic time gap, we see a similar pattern as with constant time gap. The mean and standard deviation of time gap error is reduced with coaching. The coached error is a bit higher compared to coached constant time gap, going up to 0.08 and 0.3 seconds, but still comparable. We also did this test with a stock adaptive cruise controller. It performed with slightly higher standard deviation than the average coach driver, approximately middle of the pack as compared to the 6 coach drivers. So where does that leave us? Well, we have these 3 conclusions. 1, an HCPS that we call CanCoach that's effective in achieving precise control objectives. 2, this demonstration of a true HCPS. And 3, the ability to do it at a low cost, so it's scalable. This solves our problem. We have a functional actuator that can precisely follow longitudinal control tasks as devised by the traffic engineer. Looking forward, we are interested in deploying CanCoach on a large number of vehicles to control bulk traffic. We've started testing reusing the CAN-to-ROS framework to send commands from tuned cruise control models from ROS. And we're planning on testing AV controllers safely with ghost mode. You'd rather run your experimental controller into a ghost car than a real one. I'd like to close by thanking the NSF and DOE for funding this work, and thank you for watching this presentation.